Hello everyone and welcome. My name is Jason Gregerson, and in this video we're going to look at the variation of parameters. So first, what is variation of parameters? Well, it's a method to calculate the particular solution, x sub p, to an inhomogeneous linear differential equation. Now the thing to note in this definition is the lack of restrictions. So if we compare this method to the method of undetermined coefficients, one difference is here the coefficients of the differential equation do not have to be constant. Do not have to be constant. So the only thing that's required for variation of parameters to be a valid method is for the differential equation to be linear. The other lack of restrictions, as this method will work for any f of t. In other words, it doesn't matter what the function is on the right-hand side of our differential equation, variation of parameters will work. Now let's dive right into the method. So we'll start by considering this nth order differential equation in general, and then we'll look at our specific example of a second order differential equation. So step one is to calculate the complementary solution. And then the key step, the key idea that drives variation of parameters is we make an assumption that our particular solution is some function times x1 plus some function times x2, so on and so forth. So we know that xp can't be a constant times our solutions to the homogeneous equation. So instead we assume it must be some function times the solutions to the homogeneous equation. So that's our assumption. Then how do we go about finding these mystery values for k1, k2, and k3? We're going to calculate the Wronskian given our solutions, and these other determinant values, w1, w2, wn, and these will allow us then to calculate k1 prime, k2 prime to kn prime, which we can then integrate to find our k values. And then lastly, we'll form our general solution. So let's look through the details here with a specific example. So step one is to find our complementary solution. So we know how to do that. We're going to generate our auxiliary equation, and we're going to find the roots. In this case, I would have r plus 2, r plus 1 equals 0. That would tell me that r is equal to -2 and -1. And so my solution, my complementary solution, would be c1 e to the -2t plus c2 e to the -t. So in this way, I've identified x1 and x2, two solutions to the homogeneous equation. Next, we're going to calculate w, w1, w2, and wn. So what are these guys here? Well, we already know what w is. W is the Wronskian. So it's the determinant of the matrix we get when we take our solutions along the first row and the derivatives along the second row. And if there were three solutions, if it was a third order, then we need to take the first and second derivatives, so we would have three rows to match the three columns. But in this case, we just have the determinant of this 2 by 2 matrix. So specifically, I have e to the -2t and e to the -t. The derivatives being -2e to the -2t and e to the t. I calculate this determinant by taking the product of the strong diagonal, so e to the -3t minus a -2e to the -3t. The result is going to be +1e to the -3t. So there's my value w, the Wronskian. Now what about these w1, w2 to wn? Well, w1 is going to have the same form like the Wronskian. It's going to be the determinant of this matrix, except the difference is that the first column will be replaced by 0 and f of t. And the second column will be like the Wronskian. It'll be x2 and x2 prime. So in this case, I have 0 and e to the 2t, because that's what the right-hand side of my differential equation was. And then the same second column from the Wronskian. So this would be e to the -t and the derivative -e to the -t. Similarly, w2 will be just like the Wronskian, except that the second column will be replaced with 0 and our function. So the first column will just be like my Wronskian, and the second column will be 0 and e to the 2t. And if this was a higher order differential equation, we have w3, w4 be formed a similar way. We would take the general Wronskian and replace the ith column with all zeros with the last entry, which would be the function from the right-hand side of the differential equation. All right, so now we can calculate W1 to be 0 minus e to the positive t. And we can calculate this determinant for W2 to be e to the 0, which is 1, minus 0 times something, which is 0. So W2 is a value of 1. So now we've calculated W1 and W2. Now we can form our values for K. In this case, since K1 prime is W1 over W, I know that K must be equal to the integral of W1 divided by W. So in this case, I'm integrating W1 negative e to the t divided by my Wronskian value, which is e to the negative 3t. I can simplify this by saying this is negative e to the 4t dt, and I'll get a value of negative 1/4 e to the 4t. So this would be my value for K, K1. What about K2? Well, I have my formula, so this will be the integral of W2 over W. So in this case, I have the integral of 1 divided by e to the negative 3t, which means I'm basically integrating e to the 3t, which should leave me the result of 1/3 e to the 3t. Now I basically have all the pieces that I need here. So I can jump right to forming my general solution. My general solution should look like my complementary solution. So that'll be C1 e to the negative 2t plus C2 e to the negative t. And then I have plus, well, I have K1 times x1 plus K2 times x2. So K1 is negative 1/4 e to the 4t. So that's K1 times my x1, which would be e to the negative 2t, plus my K2, which is 1/3 e to the 3t, times my x2, which is e to the negative t. So I've kind of just dumped everything into my general solution here. And then lastly, I would simplify this. So I'm going to have C1 e to the negative 2t plus C2 e to the negative t. I'm going to see if I can consolidate this. I know that if I have e to the 4t times e to the negative 2t, that's going to be e to the positive 2t. And actually the same result will be over here. E to the 3t times e to the negative t is also e to the 2t. So then I'm basically taking negative 1/4 of the first guy plus 1/3 of the second guy. I can put those over a common denominator of 12. And this would be telling me negative 3 plus 4 in the numerator. So it looks like I'm going to have 1/12 e to the 2t. So all that simplifies to be plus 1/12 e to the 2t. And this then would be my general solution to the inhomogeneous differential equation. All right, so if we recap our steps, step 1 was to find the complementary solution. That's easy enough. Auxiliary equation, find the roots, form your general solution. That tells us about x1 and x2. Then I have to form W, the Wronskian, and W1 and W2. It's best just to kind of memorize the flow of those determinants. You're sort of replacing the Wronskian, the first column of the Wronskian, with 0 f of t to find W1, and the second column with 0 f of t to find W2. Then we know that I have our formulas for the k's. So K1 prime is equal to W1 over W. K2 prime is equal to W2 over W. So we can just integrate those formulas to find K1 and K2. And lastly, we just dump everything into our final solution, our general solution of the differential equation. All right, that concludes this video on variation of parameters. Thank you very much.